Hi, today we're going to go with the second topic in higher level chemistry, option D, which is nuclear medicinal chemistry. All right, and so you may recall from Unit 2 that there are such thing as radioisotopes, sometimes called radionuclides because we're talking about the nucleus, we're focusing on that. Radioisotopes are isotopes of a particular element that are able to produce nuclear radiation, that they can emit nuclear radiation of some sort. Namely, the most common ones are going to be alpha emissions, beta emissions, gamma rays. Sometimes we'll also have positron emission or proton or neutron emissions. Okay, so what do we use these radioisotopes for? In medicinal chemistry, we are going to use them as one of two things: either tracers, so basically by following the emission and the location of the emission, the concentration of the emission, etc., we can see how the activity of a particular organ may be. It may allow us to do an image of the brain or the skull, inside the skull, because those are going to be much more difficult to see given the fact of the thickness of the bone in the skull. Or another way that we can use them is to actually treat tumors and other types of cancer. All right, because their ionizing radiation can damage cells. All right, and so what are the two types of treatment or radio treatment that we can have? Well, radiotherapy can be internal or otherwise known as brachytherapy. All right, or it can be external, where the radiation source is outside of the body. Brachytherapy, we are actually going to inject, we're going to place small pellets or wires that contain the radioisotopes into the area where we want them to act. Most of the time, the nuclear radiation, the emissions that are done, have a very small radius of action, all right, because they're so reactive that they will interact with the cells nearby, and therefore we really want to make sure that we just place them in the area where they're going to be destroying those cells. All right, those cells are going to be broken down because of the ionizing radiation. Now, ionizing radiation can do one of two things, but mostly it's going to damage the DNA. All right, and by knocking electrons from it, changing the bonds, it may cause errors in the copying and therefore trigger the self-destruct mechanism in the cell. All right. Because it acts on DNA, it's going to be acting on those cells that rapidly reproduce. Now, we know tumor cells, cancer cells, are going to be very fast in their multiplication. But so are other cells in the body, like the hair follicles, like the lining of your gastrointestinal tract, because those are areas where we have rapid turnover of cells, which of course then means that these are cells that are going to be affected when we have radiation therapy, and given the common side effects that we see of hair loss and nausea and digestive problems, because it is affecting the lining of your intestines. All right. Other cells that do rapidly reproduce are those the sex gametes, and so that's also going to be, it can for in long-term treatments cause sterility, and because it also affects how cells in general are recovering, it may cause also significant fatigue. All right, so here in this image over here we have a case of looking at some external therapy. We're going to be and we're going to come back to this in a moment, but it's just basically an overview. We're going to be emitting radiation that is focused in a particular depth where the tumor is, and it should kind of mostly attack and affect those particular areas. In brachytherapy, instead, I think I had that actually up here, we put the small bit of radioactive material within a pellet. Normally they're not much bigger than a grain of rice. All right, and it gets placed in the area where we want to destroy a tumor, and so as the cells die around it, it will allow for normal cells to continue developing. All right, and this is kind of what we see at the bottom image. Even though this is for external radiation, this can also happen through internal radiation. We are causing the lysis of the tumor cells, and there is a possibility for good cells to kind of grow back. All right, excellent. Now let's go ahead and talk a little bit about this. Now this is an image taken from your book. All right, this is the most common types of radiation are going to be alpha, beta, and gamma, but there are other types of radiation. Positron, which is the anti-matter particle for or pair for the electron, so it's positive, but it has the same mass as an electron. We can also emit neutrons, all right, and we can emit protons. X-rays are not nuclear radiation, but sometimes people get confused with that. Just kind of to give you a general idea of just what they are. X-rays are also photons like gamma rays, but they have a different set of frequencies. All right. Now, the most common techniques used in nuclear medicine, or most common radioisotopes used in nuclear medicine, are going to be either for imaging or, as I said, for radiotherapy. The first one we're going to talk about is technetium. Technetium-99 metastable, or technetium-99M. All right, is a high energy technetium. That all technetium is artificially produced. It does not exist in nature. It has such a quick half-life that it has been consumed, so we do not find it in nature. The half-life of technetium is about 6 hours. So every 6 hours, the sample that you have goes down to half its activity. We will talk more about half-life coming up. All right. Now, technetium is mostly an gamma ray emitter, and because it's a gamma ray emitter, and it happens to have produce gamma rays that have a slightly lower energy than X-rays, it makes them safer for the tissues because they don't travel, they don't produce so much damage as X-rays could do. All right. Now this is used as a tracer. All right, and it can be used for PET scans, etc., etc. All right, so some type of imaging processes. Now, how do we use it? Technetium happens to have chemistry very similar to that of a manganese. If you look at the periodic table, it is just below manganese. Therefore, it has similar chemistry. It can create a pertechnetate, all right, which is similar to the permanganate ion, all right, but it is not as a strong oxidizer as a permanganate, and so therefore it's a nice soluble compound that will flow through your bloodstream and actually go to the areas that we want to see. For example, if we want to see a tumor, tumors tend to have very high levels of irrigation, of blood irrigation, because they are consuming so many resources, and so it is going to be good. Now, by having a short half-life, it's something that allows us to see, to create an image, but not something that will stay with the patient for long enough to cause significant damage. It will be, it not only will it decay, but it also will be removed from your system through normal excretion. All right. Another source or a type of radiation that we use significantly in nuclear medicine or nuclear chemistry is going to be beta emitters such as yttrium or yttrium-90 and lutetium-177. Both of them are used in internal therapy, internal radiotherapy, or brachytherapy. All right, and they have relatively short half-lives. Okay, yttrium-90 has a half-life of 64 hours. All right, just a little bit under 3 days. And lutetium has a half-life of about 6.5, 6.71 to be exact, days. All right, and yttrium and lutetium are both beta emitters. Lutetium can also produce a little bit of alpha emissions. All right, and they are terrific for treating things like liver cancer. Small portion of the radioisotope is injected into the tissue where it's going to be working, beta emissions do not travel very far. They can only travel a few millimeters, so it will actually target very carefully the target cells of that tumor, for example, in the liver, and without affecting other cells in the rest of the body. All right. Lutetium is also used to treat neuroendocrine cancer. So we're talking about things that have to do with our glands. All right. And so this is actually going to be quite useful. In addition, lutetium-177 can also emit small amounts of gamma radiation. All right. And these can be used in order to observe how the tumor is changing. All right. If you have a large tumor, we can see how large it is, and as the tumor decreases in size, as it's being destroyed by the radiation therapy, fewer of those areas will be observed, and so fewer of the areas of those cells will be irrigated, and so less and less will be present in the imaging process that we have. We're actually going to be having always detectors to see how and where that lutetium is centering itself. All right, so pretty straightforward. Let's go ahead and move on. Another technique that can be used is alpha radiation. Now, alpha radiation is the most important type of application that we have for nuclear chemistry, nuclear chemistry, nuclear medicine. All right, and one of the ways that it's done, okay, is targeted alpha therapy, or TAT. All right. Now, alpha particles are very large particles. Remember, they are the nuclei of helium atoms. So they're quite large. They're doubly positive, all right, 2 positive charges. But because they're so large, because they are so positive, they will tear electrons off very quickly from anything that they find. So they are not going to travel very far. They're going to travel somewhere between 50 to 100 micrometers. All right, so less than 1/10 of a millimeter. Remember, we talked about beta particles. They tend to travel a few millimeters, so something between 3 to 5 millimeters. This is going to be taking less than 1/10 of a milliliter. All right, now you cannot use alpha radiation externally. It's absolutely impossible, because it just does not penetrate deep enough. All right, but used inside, injected into those little wires or pellets that get placed into the tumors, they are absolutely terrific. All right, now common things that we use for targeted alpha therapy are going to be substances such as lead-212, astatine-211, and actinium-225. All right, they are normally the radioisotopes are connected to some type of monoclonal antibody, or something that will target a particular protein, a protein that is going to be present in the receptors of the surface of cancer cells. So this makes it very, very selective. The radioisotope only will bind to those cells that have those receptors, to the cancer cells. And so because the radiation can only travel a very small distance, only that cell and those in its immediate vicinity could possibly be affected. And the likelihood is that those in its immediate vicinity are also going to be tumor cells, all right, cancer cells. And so it reduces damage to the surrounding cells, to healthy cells that we do not want to have. In addition, if you actually connect it to an antibody, those cells may have metastasized, those tumor cells may have metastasized and be in other parts of the body. Well, this TAT, this targeted alpha therapy, can actually find those receptors of cells that have traveled through the bloodstream to different areas of the body, and also keep them. So it is actually one of these very promising therapies that are being continued to be tested and developed. All right. Now, another thing that is, as mentioned before, is that tumors, because they're rapidly reproducing, they are going to need more blood flow. And so anytime that we can put a particular drug that will dissolve into the bloodstream, such as, for example, radium-223. Right, that has a little bit of a longer half-life, 11.4 days. All right, if we can put it into the blood and into the bloodstream, radium is in the same family as the alkaline earth metals, all right, as calcium. So therefore, it can get incorporated in areas where calcium would get incorporated. And so one of the most important places is your bones. And so radium can be used as targeted alpha therapy for special types of bone cancers, especially things like leukemia as well, because that's going to be happening within your bone marrow. So those will be acting closer to the right areas. Okay. All right. We're going to move on to talk about boron neutron capture therapy. My Lord, what a mouthful. All right. BNCT. All right. Now, boron neutron captured therapy, all right, is something that has been developed, okay, using boron 10. Boron 10 can actually absorb neutrons and go from boron 10 to boron 11, all right. Now, boron 11 emits alpha radiation. So what it's done is we supply the body with boron 10, all right. And only certain tissues, we're going to make sure that we are injecting into the particular tissues that will absorb that boron 10, all right? And then we radiate the body with neutrons. Now, neutrons tend not to interact with matter too much. But if they find boron 10, it becomes boron 11. It can emit alpha radiation and kill the surrounding cells. So only the cells that contain boron 10, which we have targeted particularly, will actually be the ones that be affected, all right? And so the way that we use this is that we create a boronophenylalanine, all right? My Lord, can't say any words today. And that will be incorporated because it's so similar to the normal phenylalanine amino acid that it will be incorporated into the proteins of rapidly reproducing cells, all right? And so because those are going to be present more in the tumor cells, the cancer cells, then when we radiate with neutrons, those are the cells that are going to be emitting alpha and being destroyed. All right. So here we have a little example of what the reaction would look like and what is the shape of the boronophenylalanine molecule. All right. So here we've got our boron 10. When we add a neutron, it becomes unstable boron 11, which will emit alpha and leave some lithium, and also some gamma radiation will be emitted. All right. So this is quite nice because that alpha particle, all right, that nucleus of helium is the one that can then destroy those tumor cells. All right. Borophenylalanine is like phenylalanine, but it has over here added this borono group with these two hydroxyls attached to it. Okay. Another technique that is used in nuclear medicine is the gamma knife. The gamma knife is an external type of radiation, all right, and it uses gamma rays. It's obvious from its name, gamma knife, all right. Now, each particular gamma ray, even though it has a very strong penetrating power, does not have a very significant ionizing power, so does not create a lot of damage. But if we can use focused gamma rays, and so they overlap in the same spot, we can do this by focusing the rays from different emissions using a particular type of machine, which has a kind of like a shielded helmet that allows only radiation to come through at particular angles. And we use cobalt 60 as the gamma ray emission. All right. Then those particular cells where it crosses over is going to have multiple gamma rays, and that is going to have more energy, which will kill those particular cells. We are going to then have all the rays overlap in the area of the tumor to actually destroy those tumor cells. All right. So it's actually a very strong, very targeted, very careful, and very precise instrument that has been created. Now, obviously, the way that those angles change and all these kind of things is done through computers, and it is aided by the use of other imaging techniques, whether they're nuclear or not, which we'll be talking about in just a moment. All right. Some of those techniques that we use in order to visualize things are can be called radiodiagnostics. All right. We can use CT scans and we can use PET scans. All right. Positron emission tomography and computed tomographies, which are actually to be able to see inside of our bodies, inside of our brains, our heads. All right. CT uses X-rays. All right. While PET scans uses positron, okay, positron emission tomography. And so both of them are very powerful tools, but CT scans, because it's X-rays, is something that we can turn on and off. PET scans, you have to inject the patient actually with some type of radioactive material, all right, either light water that contains oxygen 15, which is a positron emitter, or you can use as a modified form of glucose that contains fluorine 18. Fluorine 18 as well is a positron emitter. Now, when a positron and an electron find each other, they annihilate themselves, that all the matter becomes pure energy, and that comes out in the form of two gamma photons. And those gamma photons, depending on the angle and where we actually have our receptors, can give us ideas of where that blood flow is going, and therefore help us create an image, a three-dimensional image of where the blood flow is. And remember, tumor cells have increased blood flow because they require that in order to continue growing. All right. We can use also iodine 131, okay, in order to map, and that's particularly because iodine settles in your thyroid, all right, as we talked about in Unit 2. And so we can use iodine 131 both to image, or if you have a larger dose, to actually treat thyroid cancer or cases of hyperthyroidism, all right. One other way of doing imaging is called MRI, magnetic resonance imaging, which actually uses, all right, nuclear magnetic resonance, all right, hydrogen or H1 NMR. Just like we talked about in the organic chapter, this is the same basic idea. It does not use any nuclear radiation, but it does use the spin of the nucleus, all right? That's why it's nuclear. It's still nuclear chemistry, but it's talking about the nucleus itself, and when it's hit with radio frequencies, it can actually give you information. Now, those nuclei are in hydrogen atoms that may be in water molecules or other compounds that contain hydrogen. Pretty much every compound contains hydrogen in the body, all right? And so we can get an idea of the different environments, and from that create a three-dimensional image of the process. Now, the wonderful thing about MRI is that it's non-invasive. It does not have radiation, so it's a little bit safer in terms of compared to CT scans or PET scans, because those have ionizing radiation, but it tends to be a little bit more expensive. All right, the price has gone down as the technology has improved. All right, so this is the part where we're talking about all of the use of radioactivity in medicine. And now in the second part of this video, which we'll cut to go to the next slide, we'll talk more about the properties of nuclear decay, the type of reactions that take place, and the kinetics of nuclear decay. All right, so stay tuned for the second part.